Okay, so hello everyone. My name is Ashley Bettis. I'm a rising sophomore at USC studying computer science and game design. Thank you all so much for coming to USC Viterbi's virtual robotics open house hosted by the K-12 STEM Center. Today, the theme is physical assistance and physical therapy. And presenting today will be PhD students Nathan Dennler and Lauren Klein. Before we start, I want to go over a few house rules. Everyone will be muted during our presentations out of respect for our presenters. If you have any questions, you can use the raise hand function to let us know, or you can also feel free to just type out your questions in the chat. That's all. Nathan, if you want to begin.
Sure. One sec. All right. Can everybody see my screen? Great. So I'm Nathan. I am from the Interaction Lab and the Icaros Lab at USC, and I'll just talk a little bit about some of the physical assistance project I've been working on, which is like robotic hairbrushing. So first I'll like explain sort of at a, a general level what the problem might be. So as people get older, there's like a higher likelihood of activities that you might have found to be very easy becoming more difficult. So things like walking, eating, or dressing, or like anything else you might do as part of your daily routine. And this can be from like a wide variety of reasons. So there might just be joint deterioration as you get older. This, like in the extreme case, you can have arthritis. There might also be some like mental deterioration that might make it hard to do day-to-day activities like dementia. And there might also be something like a very severe event that happens that can like drastically change your ability to do things from day to day. And there can be many other reasons that you might not be able to do something as easily as you used to be able to do something. And it's also kind of difficult to get help. You might have family members that can help you out with something, but maybe they might be working sometimes, or maybe they live too far away to get to you in the event of emergency. And also like assisted living can be very expensive, especially for families that are not as high income. So it can be a financial burden on people. And there's also sort of the emotional attachment that people have to the home that they've grown up in. So if you try to relocate people to get help, there might be some emotional toll about not being in the place that they find comfortable. So why we would want to keep people in their home is to sort of like mitigate all these problems and make sure that people are like happy. So one way to do this is through robotics. And when we were interviewing people who have difficulties doing day-to-day activities, there were a lot of people that actually said, what we want a robotic arm to do would be to brush our hair. Because it's like one of the first things that people see when we go out to like socialize with people back in the day of being social. And having a robot arm would help people who have difficulty lifting their arms like above their shoulder level, for example. So here's just a quick video of a preliminary system that we've developed for hairbrushing. So now that you've kind of seen how that interaction works out, I'll kind of just go and explain the different parts of the system and how they all work together to have this interaction that might help somebody brush their own hair. So the first and most important part is the person in the system. So if we don't have a person, we can't brush anybody's hair. And we also want to make sure that the person has a lot of input into the system to make sure that it works in the way that they want it to work, and is like robust to errors. The second most important thing is the robotic arm. For this project, we used a Jayco robotic arm, which has sort of 6 joints, so it can kind of go to any orientation or position in space. We also have a copper-coated comb, which we can use for touch sensing. And the reason it's copper is because copper is conductive. So if you touch the copper, it'll change the capacitance of the copper. And the Arduino that we have can also read that, and we can stop in the event of like unwanted skin contact. We also have a camera that can sense the scene that we're operating in. And the last thing we have is a computer to do all the processing of all the different parts and help the communication between the different parts of the system. So yeah, I'll get into the sensors. The first thing we have is the Kinect camera. And what you would get from this is an image that looks like this. And this image consists of like a couple channels that we're used to. So we have like the red, green, and blue channels, which they all add together and you get the color that you usually see. But with a Kinect camera, we also get a depth channel. So for every pixel, we have a value of how far away that pixel is from the camera. And then we can use this to sort of understand how the scene is and like if something's really far away or close and how we can actually get to that point. And like another side note is that like the Kinect being such a low cost is like kind of an amazing thing, because before the Kinect was around, depth cameras used to be like on the order of like hundreds of thousands of dollars, and they used to not work very well. So with like the gaming industry like creating this product, it actually helps a lot with like the affordability for just people in their home. And then in terms of the capacitive touch sensing, we have this comb that's made of metal and it connects to our Arduino. And we also have this other capacitor here between pins 9 and 8. And when there's no one touching, there's a certain level of capacitance, that's our baseline. And then when we do have somebody touch the comb, then the capacitance level changes and we can interpret that as somebody touching an object. And what's important about this is that it only reacts to conductive materials. So if you touch it with your skin, it'll sense the touch. But if you just touch your hair, which doesn't conduct electricity as well, it doesn't register a touch. And then we also have sensors inside the arm. So we have, for every joint on the robotic arm, there's a motor inside, and each motor will consume a certain amount of current to make sure that the arm doesn't just fall down and that the motor stays in place. So for example, if we have just the arm by itself, there will probably be something like a medium amount of current going through this motor, which corresponds to like a medium amount of torque, which corresponds to like a medium amount of force exerted at the tip of the arm, which we call the end effector. And then here, since it's not as far away from the tip of the arm, it has like a little bit lower force. And then as we get closer, there's less and less force. So we use this kind of as like a baseline to see like how much force might be exerted by the arm. And then if we do something like grab something light, like a comb, then maybe the force at this joint would go up a little bit. The force here would go up a little bit as well. But the force here might not change as much, since the force is related to how far away the object is and its relationship to the axis of rotation of the joint. So this joint rotates sort of like in and out of the page. And this arm kind of doesn't really have much distance from that axis of rotation. So the torque change is very small. But if we have something like someone pushing against the arm because maybe the arm isn't doing something that you want, you'll get like a much higher change in force at these joints. And you'll also get like a little bit of a change of force here. But again, since the distance between the places that the force is applied and the axis of rotation isn't very big, you'll have just a little bit of a change rather than like these very drastic changes here. So now I'll talk a little bit about how we plan the path through the hair. So first you get an image from the Kinect, and we just like plan on the 2D image first. So what we'll do is we'll have somebody pick a point in the hair. So for example, if they choose this point here, then we'll look at sort of the local area around that point, and you get this image. And then you can kind of see that there's an overall direction that all these like strands kind of flow in. Yeah, thanks. Just like that. Um, and you see that it kind of goes down into the right. And then you can take this direction and add this to the image. And now we have a new point that we're at. And then once we're at this new point, we can examine the local area around here. And then we get another image, but you can kind of see that in this image, the overall direction of everything goes down. And then we add this to the image, to the path. And then we continue to check throughout the hair. And at each point, we check the local orientation of the hair, and we follow that orientation until we get to the end of the hair. And then what we do here is we want to send meaningful points to the robot. So we take all the points that we inspected, and we tell the robot to move to each of them in order. And we get the depth from the depth channel of the camera, so that we can get like 3D positions in space. And then we have the robot go to each one in order, and that is a trajectory for the robot arm to go through the hair. So then just like putting everything together, this is sort of how the interaction works. So first someone will choose a point in their hair that they want to comb by clicking on it. Then we create this path, and then this is the point cloud that the Kinect sees. And we propose the path to the user, and we say, is this what you wanted? Then hopefully they'll say yes. And in that case, the arm will move through the path. And then it will also be checking to make sure that there's no unwanted collisions on the way, or there's no like unexpected forces. So like if you hit a knot in the hair, then you'd want to stop. And if you like hit somebody's arm while you're moving to somebody's head, you'd also probably want to stop, because maybe you're not moving towards where you think you're moving to. And then once it successfully goes through the hair, it will move out of the way, and then it will be ready for the cycle to start all over again. And someone can just choose to click another point of the hair. And this continues until the person has successfully brushed their hair, at which point they kind of stop. So that's kind of most of everything for the system. Does anybody have any questions about like how anything works, or how robotics is in general?
You have a few questions. So the first one is the way you map the head shape, is it like the slam method in any way?
Yeah, so we we can use something like the SLAM method to create like a sort of like a 3D volume of the head. But what we do is we just use the image itself, since the image might change from time to time. So if we have a model, we'd also have to figure out the orientation of that model, which can sometimes take a little bit of time. So what we do is like we just take an image like right before we want to brush the hair, and use that as our like surface that we plan over.
Kind of related, how well does it work when a person moves?
Oh yeah, so it doesn't check to see if the person's moving like while you're brushing the hair. So we assume that the person will stay relatively still. Um, but if the person moves like in between, like if they turn their head because they want to brush a different part of their hair, then we'll just like take an image again right before we brush the person's hair, and use that.
How does it check for object collision?
That's another good question. So we have like all the obstacles set up in the scene. So if we have the robot on a table, we'll have like the table, and we have the robot arm itself, and we can have like sort of like a dummy model of that head. So like just like a sphere where the person is standing. And then what we do is at every like when we're planning, we put the robot in that position, like, and we imagine what it would look like. And then we see if like if any of the joints or links, which are like the parts that connect the joints, we see if those are intersecting with any of the objects in the scene. And if that is the case, then we say that's not a valid configuration, because we'll be sort of breaking the laws of physics because we're going through objects. And then that's sort of how we check to see if there is a collision. So as you can imagine that like as you get really complicated environments, then it might take a long time to check between like every single object and every single link of the arm. Um, but for most of the time, we have like relatively simple environments where it's like just a person and a lot of like empty space and maybe a table that the robot arm is on.
In the meantime, while everybody thinks of questions for Nathan, I'm going to be launching the poll. So if you could please fill that out, it would really help us out. Thank you. Lauren, if you want to get ready for your presentation, and then at the end, we can take questions for both of you again. Lauren, are you ready to start?
Sure, yeah. Should I go ahead?
Yeah, go ahead.
Awesome. Let me share my screen. Okay, can you see my screen and hear me? Awesome. Let me throw this on present mode. Okay, well, hi, everyone. I'm Lauren. I'm a second-year PhD student. I'm actually in the same lab as Nathan, so I know him well. Thanks for that great presentation. Today, I'm going to be talking about a robotic approach to training infants to kick more often. And just to briefly motivate this problem, infants make what are called exploratory motor movements in order to learn how to navigate their environment. But for some infants, like infants who are at risk for certain types of developmental issues, these movements don't come as easily or as often. So we've developed an experiment to try and see, can we encourage infants to kick more often? And so that's the question we're kind of exploring in some of this research. And so I'm gonna at first just kind of show you guys what that experiment looks like, so you can see kind of what the robot is doing and what the infant's doing in response. Can you see the video? Okay. So first we have what's called a baseline, and this means we don't have the robot do anything, so that we can see how the infant is going to behave without any sort of intervention. Contingency phase. April 5th. So then we do a second baseline just to see, again, now that the infant's gone through this experience, if we have the robot stop again, what will the baby do? And we actually see that the baby's kind of gotten used to the robot responding to him. So we see sometimes the infants get a little bit upset or fussy or even start to cry during the second part when they notice, hey, the robot's not responding to me anymore. Great. So that's the user study protocol that we ran. So let's talk about a little bit what was happening. So part of the reason I really have been enjoying this PhD program is that it's very interdisciplinary. So this project has actually been a joint project between my lab, the interaction lab, and the infant neuromotor control lab. So my lab puts together kind of the robotics side of things, so everything you see on the left side of the screen. And then the infant neuromotor control lab takes care of that right side of the screen. So what's happening with the infant? What does it mean? What can we learn from all the data we're collecting? So you might have seen the word contingency at the top of the screen a few different times. So just to kind of, I know it's a robotics talk, but just to give a brief description of what that means. Every time the baby kicked at a certain speed, the robot kicked also. So part of what's happening there is called contingent learning or a reward. So babies really like to see things move. They find it interesting. So every time the baby kicks, the robot kicks right after. So the baby is rewarded by that. And we actually found that for about 75% of the infants in the study, they kicked more often during the contingency part, during that middle part of the study, than during the first 2 minutes of the study, that baseline. And we think that this means that the babies learned from what was happening, that they were getting rewarded, and so we saw them kicking more often. The other part, that the reason that we have a robot that's kind of shaped like a human doing this, is that in your brain there's something called mirror neurons, or a lot of little things called mirror neurons. And that's what gets triggered when you see someone doing the same thing as you, or when you see someone kind of who looks like you. The baby sees the robot kicking and recognizes that, okay, that's a leg and the baby can kick too. So we actually found in this research also that about 75% of the babies were imitating what they saw the robot doing. And that action that the baby's seeing is that kicking action of the robot. So now let's talk a little bit about the robotic system. So this is what's called a closed loop system, and I'm going to explain what that means. So these sensors that we see on the baby's leg measure for us whether or not the baby has kicked. So we measure how fast the baby's leg moving, and if the baby's leg is moving faster than a certain amount, 3 meters per second squared, for those of you who have learned about acceleration already, that sends a message over the internet to this computer right back here. So it says, okay, here's the acceleration. Computer says, okay, is that acceleration high enough? If yes, it sends a message to the robot to kick its leg. So there's a computer back here. It sends a message to a computer that's inside the robot, and then the robot computer triggers a motor in the robot's knee to move, and that kicks the robot's leg. And then that sends a message back to the baby, because the baby can see what's happening with the robot. So we close the loop, and obviously we can't control what the baby is doing. But in human robot interaction, which is the field that me and Nathan are both in, this is what a closed loop system is referring to. So to talk a little bit more about the hardware, again, we talked about this sensor that's on the baby's leg. That's called an accelerometer. So maybe some of you who have taken physics know about this already, but inside of this little box are very tiny groups of bees. So an accelerometer kind of works like this. Let's say this is the baby's leg, and the baby's leg moves up. Since it's happening so fast, there's like a tiny spring inside there that gets compressed right when the baby's leg moves up. So the little sensor can tell, okay, this spring or slinky is getting compressed. That changes some of the I want to say the resistance inside there, but maybe some of the teachers at home are correcting me. But when the spring gets compressed, it triggers an alert that a certain amount of acceleration is happening. And vice versa, if the baby were to move their leg the other direction, that spring gets pulled. And so this is kind of a very high level overview of what's happening inside of there. But that's how we measure how fast a baby's leg is accelerating. So another thing that's happening on here, there's quite a bit of different components in this system. You see, what is this crazy thing on the baby's head? That's a head-mounted eye tracker. This one's made by Positive Science. So we designed a lot of the stuff going on this side of the screen, but we bought the eye tracker. So basically what's happening here is, in addition to understanding what's happening with the baby's leg, since we can't interview the babies later to ask about their experience, obviously, we go back and see where were they looking at the different parts of this experiment, what were they paying attention to, what got their attention, when were they distracted. So we kind of want to know where their attention was drawn to, so we use an eye tracker. So it's kind of crazy how this eye tracker works, but it has two different cameras. So this camera looks out into the environment, so you can see this is maybe the environment scene, and this would be filming the robot. And then this camera looks at the baby's eye, and so it recognizes, and you can see this in the little box, it recognizes the location of the baby's pupil, and then it also looks for a little reflection in the baby's cornea. So it measures the angle between these two little dots it detects, and based on that, it says, okay, this is the angle into the world, into that scene camera where I think the baby is looking. And then we get this kind of cross on the world image or on the scene image, and we can say, okay, like, what is that object behind the cross? And so we can kind of tell based on that where the baby might be looking, and then we can say, okay, the baby was or was not looking at the robot in different times. And then based on that, we can make decisions. How should the robot act so that we can get the baby's attention more often? Or when was the baby looking at their parents, and what does that mean? And for those of you interested in this robot, because he's a pretty cool looking guy, this is the Now robot. It's made by Aldebaran, and we use it a lot because it's pretty easy to program. So if you're on the computer science side of robotics, you don't necessarily want to be making your robots from scratch all the time. We have a few in our lab that we've made from scratch, and we're really excited about those. But if you want a robot that's kind of easy to program, that is already programmed to interact with people in a certain way, then it's nice to use off-the-shelf ones. And Now is a pretty common one that's used for research in universities. So if you're interested in doing some university human-robot interaction research, this is one that you might be familiar with. And also it has the advantage of being kind of the size and shape of a baby, so it fits really well into this booster seat and triggers those mirror neurons, as we discussed before. And that's it for me at the moment, so I'd love to field any questions that you guys might have. Stop sharing for a sec.
Lauren, did you try any research with other robots other than the Now robot? I'm just curious if you had different interactions with the babies that you were using with one robot versus another.
That's a great question, and good to see you, Mr. Summy. Quick shout out to my high school calculus teacher, everyone. Yes, yes, Mr. Summy, we actually tried a similar experiment with spherical robots, which are called Sphero. You might have seen them in the little BB-8 robots that have been made in their collaboration with Disney. So we tried something similar with reaching instead of kicking, where the robots would roll around and do different lights, and we would sense if the babies were grabbing these Spheros or these robots, and then have them move in different directions to see how should they be moving around and what should they do to try and encourage the babies to move more. This was pretty difficult, actually, because it's hard to design for someone you don't quite understand, and it turned out that actually the game of I'm going to throw this robot on the floor and make the researcher pick it up for me was a lot more interesting to the baby than some other activities that we were trying to get them to do.
Thanks for that.
You're welcome. Thanks for coming.
Lauren, you have another question from Juan. How much time have both of you put to your respective projects currently?
Sure, good question. Nathan, do you want to go first?
That is a good question. I guess probably over like 200 hours, maybe. I'm not sure. It's like it's like a full-time job, so it's a lot of time, but it's fun.
Yeah, to echo Nathan, this is, I would say, one of two projects that I've mainly been working on. So I spend about half of my time on this project, and then the other half of my time I'm working with a local children's hospital to analyze some of their data on how infants interact with their mothers. But yeah, to echo Nathan, I don't know the total number of hours, but in general, when you're a PhD student at USC, you have sometimes what's called an RA-ship or a research assistantship. And that means that about half of your time, half of your work week, so about 20 hours a week, you are working in the lab. And some of those hours are dedicated to programming the robot. Sometimes it's analyzing the results that you're getting. Sometimes it's mentoring undergraduate students to work on these types of projects. So to give a concrete answer to you, about 20 hours a week, and I've been working on this project and similar projects for about 2 years.
I have a question. I have a question for Mr. Summy and Lauren. And Mr. Summy, did you recognize in Lauren back when she was in your calculus class that she had the potential to do this? And Lauren, did you imagine yourself doing this? I know that we have a lot of high school students listening in, and I'd love to sort of hear from the teacher's perspective and also the PhD student's perspective. Did you imagine this?
Lauren, I'll let you start if you'd like. Did you ever imagine that you'd be where you are?
I would say half and half. So Mr. Summy, I don't know if you remember my college essay on L'Hopital and how I too like to look at fractions and limits in a different way to solve problems. But I did apply to engineering schools with the help of Mr. Summy. And I wanted to do mechanical engineering, which I did end up majoring in as an undergraduate student. I liked both mechanical engineering and computer science and couldn't really choose, and a great advisor of mine then directed me towards robotics, which is how I found human-robot interaction. I worked with Guy Hoffman at Cornell, who's an excellent researcher. I recommend you check out his work. I was doing human-robot interaction, but decided at that point I did want to switch over to the computer science side of things. But it is mostly math, which is what I was doing throughout a lot of high school most often. Most of my classes by senior year were predominantly math-related classes, and that's most of what I did in college, but it definitely shifted around through a few different areas of research and a few different areas of study throughout college. All right, Mr. Summy, did you think I had the guts?
Well, the guts is the easy part. Yes, absolutely. I think the piece that always struck me about Lauren was she was always willing to kind of talk the nerdy, the deep, the go further kind of question, not just the surface or the skill that maybe we were learning. I think the other thing about Lauren that is often very unique from a teacher's side is that she wasn't just interested in the math. She was always interested in how things kind of connected to other areas. She was very diverse in her interests, at least from my perspective. So she went very deep with the math, but she also kind of spread her interests around. And so if you were going to ask me, could I see her doing a PhD program in USC when she was a junior in high school or a senior in high school, I would say, I don't know. But I know that the math was absolutely, she was always, far and above kind of local peers within that group. There were other students that were standouts too, but Lauren, because of knowing, getting to know her a little bit, it doesn't surprise me that she's where she's at. Not at all.
Thanks.
I have a question. Oh, Katie.
I was just going to say, should I ask if there are any other teachers of Lauren's? I'll let Ashley go ahead.
Okay, so my question is, what are the next steps for both of your projects, if you know already?
Sure, so I can take this one first. So with this project, the goal is now to do a bit more of a machine learning based analysis. So we have some great collaborators from the infant neuromotor control group who have been coding what the infant's behavioral state is at each time. So the baby is either alert, fussy, or crying. You didn't really see it in this video because for those of you who don't know, demo videos are always the best case scenario. Nathan can attest to that, I'm sure. So the next step is, sometimes the babies get really upset when the robot is not kicking. We've done a few other experiments where the threshold's a bit higher because we want to see if we can get the babies to kick faster. And this is very upsetting to some babies who don't kick fast enough and then don't have the patience to handle that. So our goal is to see, can we predict in real time based on the infant's facial features and based on the infant's pose features and vocal features, can we predict what their current behavioral state is? And based on those features and what's happening with the robot, can we predict what their next behavioral state's going to be and whether they're going to be able to engage with the robot? And can we predict that in real time? So that's the next step for this work, is that machine learning based analysis.
Yeah, and then for me, I guess our next step would be to, we have like some other methods to plan trajectories through the hair. So the other one that we use is basically just goes like straight down on the mesh that we create of the person's head instead of using the picture. So we were gonna test with like actual people, sort of seeing which one they prefer and which one's better in terms of like their experience, and even if they notice a difference at all. And then after that, the thing would probably be to not just like follow the direction that their hair currently is in, but also have some way to input the kind of style that they want to change to, which maybe doesn't go exactly with like the way their hair currently is falling.
I'll read out the question for you guys. So before creating and programming the robot, how much research was looked into before doing any of this stuff?
A lot. So when you're doing a research project at a university, it's usually it has to be funded by someone, right? So usually you are applying for that funding. So you write what's called a research proposal, which is a 10+ page document, and you write about the research you're going to do. So you have to explain to someone who's going to then give you money, what are you going to do? How is it going to be helpful to the world generally, and also the research community? So if you are doing computer science research for babies, you have to explain how is this going to be helpful for babies eventually, and also how is this going to be helpful to other computer scientists who are looking to do something similar to you, or looking to do machine learning and hoping to learn from what you've done. So that takes quite a while, and often you'll propose something, it'll get rejected from some place, you'll propose it again, and it takes a couple of years sometimes to get proposals through. So it takes quite a while.
Yeah, and agree. Just to just like add on to that a little bit, you also have to like make sure that like the thing that you want to do is actually feasible. So like a lot of research goes into making sure that you can like sort of have a roadmap of what you'd want to achieve before you actually like start and go out trying to do something. You don't have to have like a totally clear path, but you kind of have to have like an overall idea of like the parts that need to work together for something to achieve what you wanted to achieve and like actually help people.
Mm-hmm. I see someone ask, what's your budget for making the robot? Our robot was off the shelf, which means we didn't make that, and I believe that's the case for Nathan's robot too, though you can correct me.
Yeah.
And now all the bar on robot can range from around $4,000 for an older one to above $8,000 for a newer one. So it depends kind of on how you buy it, and occasionally companies will give discounts for research groups, but it's pretty expensive. So again, in those proposals, when you're proposing doing this type of research and planning it out, you plan your budget, and you have to kind of explain how much of that is for equipment and different materials. But yeah, research robots can be quite pricey. But if you're interested in doing robotics at home, there's a lot of great options. The Sphero robot that I was talking about earlier does a lot with different classrooms, and that's about $250. There's a lot of great Lego options for different high schools, and Bex Robotics is accessible for some high schools. So if you're interested in your own budget, there's definitely a lot of options if you're interested in playing around with robotics. Nathan, how much was your robot?
Yeah, so in general, like robotic arms are very expensive. The one that we have is like $30,000, I think, which is actually like pretty cheap. Like a lot of them will be like hundreds of thousands of dollars too, I think.
Mm-hmm.
And yeah, I agree with Lauren. There's a lot of like cheaper options if you can't just drop $30,000 for a robotic arm.
Nathan, I have another question. So a lot of challenges, like STEM challenges or robotics challenges, involve creating a robotic arm. Obviously, like a high school team doesn't have $30,000, but do you know that making a robotic arm, or making, you know, a first robot that can throw something, or a FRC that can throw something, are those skills similar to what you have to do? I mean, is that a good sort of first step for learning how to do what you're doing?
Yeah, definitely. So like there's a lot of like algorithms that you use on arms in general. So like things like we call them like forward kinematics or inverse kinematics, to like figure out what joint angles you have to give to the arm to make it reach a certain position. The formulas for these apply like across any kind of arms. Like if you have like 3 joints or 6 joints or 7 joints, you can use sort of the same algorithms to do planning. So you can like learn on something that you've made yourself. So in my undergrad, actually, there was a lab where we had 3D printed arms that we like programmed to go to different places. And I've used like the same kind of algorithms that I used back then for this arm.
Nathan, you have another question. What if there's a knot in the hair?
Oh, if there's a knot in the hair. So right now what we do is we just have the robot stop so that we don't like yank people's hair out. But I guess in the future what we would do is like maybe find a way to mark where that knot is, and then like brush around it first to like detangle it a little bit, and then like continue from like the top to the bottom. So like instead of like starting all the way at the top, if the person clicks there, maybe we would start like where we know the knot to be.
Nice. I've employed that method myself.
Nice.
Another question I have is, how did you guys decide that you wanted to do a PhD? And also, do you have any advice for high schoolers or anybody else who might be considering doing a PhD?
Yeah, so for me, I kind of wanted to go into teaching at some point. And if you want to like teach at like a university, then you kind of have to have a PhD. In terms of like things you can do during college to like, if you're interested also in applying for a PhD, you can like try to get into research at your undergrad institution with somebody as like someone who helps out with some studies, and like getting publications like pretty early, I think is helpful for getting into grad school. And also like taking classes that you find interesting and relevant to like what your like field of interest is always helpful too, I think.
Yeah, I did not want to do a PhD at first. I was looking at master's programs, and then had been doing research, and over the summer worked at the Jet Propulsion Lab for a summer, which is a branch of NASA that does a lot of robotics research. And most of the people there had PhDs, and I saw a lot of the doors that it opened and thought that that was really interesting. So then I talked to my advisor about different options, and he actually connected me to my current advisor, Maya Matarik, at the Interaction Lab at USC. And I met with her and just was really excited about her research, about robotics and about kind of the intersection of robotics and healthcare and human robot interaction. And so decided my senior year that I was interested, and so it definitely helped to have had some research experience previously when I was applying, but I didn't really make the final decision to do a PhD until second semester of my senior year of college. Someone asked, did both of you ever imagine working with physical assistants and physical therapy? Yes, actually. So when I was in my undergrad, I worked on a robotic third arm project at the point it was for construction workers, but construction workers actually get injured a lot. So we were working on a robotic third arm that could attach to maybe their lower back or a different area that would kind of move the load to a different area of their body, and reach into kind of dangerous spaces, because when you're on a construction site, there's a lot of things falling, or places that are really hot, or where you could get a shock. And so I was working on a robotic third arm project and met with a few different construction workers, a few different doctors, a few different healthcare specialists. So in addition to doing the computer science side, I really enjoyed that healthcare side, or kind of physical assistance side as well. What about you, Nathan?
Yeah, for me, I guess I didn't think as much about physical assistance until I started the program. I was kind of interested in like seeing how robots can change how people like how robots can act to make people like understand what they want to do. But I think that this is a good way to kind of like uh, find a way to have robots like interact with people in like a physical way, and have them like form their opinions about what the robot's trying to do.
Mm-hmm. Someone asked if you guys ever worked with the Moxie robot. That's a super interesting question, actually, because Moxie is made by Embodied, and that was actually a company founded by our advisor, Maya Matarik. So I don't know if that's been released to research labs yet, because it's pretty new. That company recently came out of what's called stealth mode. So they recently announced what's happening with that robot, I think like a month ago max. But it's super exciting, super excited to hear more about it. But that was actually founded by our advisor and based largely on research that came out of our lab. So we haven't worked with that robot specifically, but hopefully one day. You're welcome.
Well, if there are no more questions, I guess we'll end it here. Thank you guys so much for presenting. If there's any last words you want to say, that'd be.
Yeah, I think that's it. Aside from, this is a great time to learn skills on your own if you're in high school right now or middle school and don't have too much going on with school right now. There's a lot of great online classes you can take, and if you're interested in learning about machine learning or robotics or all these different aspects of what we do, it's a great time to learn more about that.
Yeah, I just wanted to also thank everybody for coming. And I also kind of want to like talk about how I think robotics is a really great field because it's like super multimodal or like multidisciplinary. So like just robotics like as itself kind of like encompasses like computer science and mechanical engineering, and like electrical engineering. And then you can get into like with human robot interaction, you can get into like things like psychology. So I think it's like a really great field, and I hope you guys all like think the same thing.
Thank you.